All right, let's go ahead and get started, okay? We are going to start over the next 2 weeks to really bring this class together, okay? So today what we're going to do is we are going to talk about RL series circuits, RLC series circuits, okay? We're going to have our three components that we've been dealing with for so long all together in one big happy circuit. So this will be a resistor, a capacitor, and an inductor. So if you don't already, go ahead and get your formula sheets out. You can see that I have mine over here, and your calculator's ready to go, because we're not going to learn that much new here today. Okay, we have like one little step that we have to learn, and after that, it's all basically the stuff that we've been doing already. Okay, so let's go ahead and see how this is going to work. So, as you guys recall, Eli the Iceman becomes crazy, crazy important in this lecture. Okay, because when you have a capacitor, an inductor, and a resistor in a circuit, as your frequency increases, the circuit will actually move from being capacitive to inductive, okay? And so this is really, really weird. When it's capacitive, your current is leading your voltage. When it is inductive, your voltage will be leading your current. Okay, and we're talking about totals here, right? So the total voltage and the total current, and how these are in phase. And at some point, your voltage and your current will perfectly line up, and then they will go in the opposite directions again. Okay, and you'll see this when we do the lab. It's really, really cool. Okay, but let's do a little recall here. All right, so as you guys remember, in an RL series circuit, we have a number of little different things here. So this is the voltage. This could be considered your X of L, or your voltage, or your inductive power, okay? The power over your reactive component right here. All right, we're in the positive vector. Okay, so we're in vector 1. So our phase angle here is going to be between 0 and a positive 90 degrees, okay? Now, if you recall, if the phase angle was greater than 45, it was more inductive. If it was less than 45, it was more resistive, meaning our voltage drops, our resistor values are going to be higher than our voltage drop across our inductor, and our resistor is higher than our X of L. Okay? Now, if you recall, and this is a while ago, okay, so I'm sympathetic to how long it's been. It's been before midterm, before all this craziness started. In a capacitive resistive circuit, okay, our phase angle was negative, all right? And so if our R was larger than our X of C, it was more resistive, meaning it was between 0 and negative 45 degrees. If our voltage, and that would be the same for our voltage drops as well, okay? Now, if X of C was larger than R, it would be between negative 40 and negative 90. Okay, now what we're going to see here in this lecture and in the lab, that our voltage total will be able to swing between the vector 1 and vector 4. Okay, it's the combination of these, and it's all based off of our frequencies. All right, so in this circuit now, we are going to have to take into account our voltage across our inductor, the voltage across our resistor or capacitor, and how those subtract each other out. And then as the constant between all of these has been our voltage across our resistor. Okay, so without further ado, let's go ahead and get started. Now, the first thing we have to understand is that our X of C and our X of L are still calculated the exact same way with the formulas that we've been using. Okay, so we have X of L, okay, which is equal to 2 pi frequency L. Okay, we have X of C, which is 1 over 2 pi FC. Okay, so we still have those formulas. Okay, all right. Note that this is a C, not an L. It's just like the whiteboard at school. All right, so now we have to understand what the total of that is. Okay, what is our total in reactance? All right, and the formula for this, which can be identified a couple of different ways, they call it XTOT here, which would be total. All right, Some people will put X total here. Some people will put LC here. All right, depending on the writing, but it's all the same. The formula for this is X of L minus X of C. Okay, now some people say you have to keep this positive. You have to keep it positive. You have to keep it positive. And that's true, but if that value comes out negative, that means your phase angle is negative. And the only way the phase angle would come out negative is if your X of C is larger than your X of L. Okay? All right? And so I think that's, kind of that will keep it true. That's what these brackets here for, all right, to indicate that the answer would always come out to be positive. But again, that's not necessary, okay? As long as you understand what I just said, that if X of C is bigger than X of L, okay, then the phase angle is going to be negative, all right? Now, the reason this step right here is so important is because that helps us to calculate out our Z, okay? And Z is equal to the square root of R squared plus XLC here, okay? I'm going to write this as X total squared, okay? All right? Now, some people will show this formula here embedded in this formula here, okay? And you can do that, but I like to get my X total first and not type all that into the calculator, all right? So, and then here we go, our first phase angle, all right? So our phase angle here, our calculation is going to be the inverse tangent, okay? And that will be my X total over R, okay? All right, and so that's why if you keep this as a negative, if X of C is larger, then your phase angle will automatically show that it is negative, which I think is actually pretty cool. I think that's pretty cool. All right, so now voltage can be found a couple of different ways. All right, but before we get into that, you need to know how to get your current total, okay? And so your current total here can be found, as you guys know, is your voltage total divided by Z, okay? All right, and this is important. Now in lab, we don't do this. In lab, we will use this formula here, VR over R. And that will be the same because current is a current and the current in a circuit. And this can be based off of anything as well. Another way to do this is to take, like, say, your X of L, your voltage total over I keep messing up. I'm so sorry. This is just like lecture. Your voltage drop across, let's say, your inductor over X of L. Okay? Cool? Makes sense? I think so. I think it makes sense to you guys. All right, sorry, a little confusion there. So yeah, all of these will actually be able to get your resistive, your current total. But this is the one when you're doing in an ideal circuit that we're going to use the most. Okay? Then, once we get those values, okay, once we get our current total, then we can start to get our voltage drops, okay? And so what we're going to do here is voltage drop across the resistor is going to be R times IT, okay? Voltage drop across your inductor would be X of L times IT, and voltage drop across your capacitor would be X of C times IT. Basic Ohm's law. Just basic Ohm's law here. All right, pretty straightforward. And then if we wanted to get our voltage total, okay, if that wasn't known, okay, then our formula would look like this. Voltage total equals the square root of VLC squared, which would be VLC is the voltage across the inductor minus the voltage drop across the capacitor, okay? And then plus voltage across the resistor squared, okay? It's all just Pythagorean's theorem at this point, okay? It's just that extra little step of subtracting what is across the inductor by what's going on in the capacitor, okay? And all of this is based off frequency. I don't want you to forget that, right? Because this is all based off of X of L and X of C, okay? And those values are based off of the frequency, okay? All right, that is crazy, crazy important, all right? So in a series RL circuit, the circuit can be capacitive or inductive based off of the frequency, which is what I've kept mentioning here, okay? At the frequency where X of L and X of C are equal, this is called series resonance. So as my circuit becomes, my circuit's inductive, okay? Inductive and capacitive. Okay, this is where my voltages are. Let's do this, all right? So this is the voltage across my capacitor. This is my voltage across my inductor. And as my frequency changes, they start to go. The voltage drop across my capacitor starts to drop. The voltage drop across my inductor increases. And then right when they are equal, this is resonant frequency, okay? And they completely cancel each other out because, as you can see in the formula here, they're subtracting each other, okay? So let's say they're both 5 volts, okay? They're subtracting each other perfectly. And then as the frequency continues to increase, the voltage across my inductor increases and the voltage across my capacitor decreases, okay? So they're like passing themselves in the wind, okay? All right? And again, this is all based off of frequency, all right? Here and here. That's why these formulas are so very important, okay? And at resonance, okay, we're going to learn a little bit more about that because it's important to understand, because at that, you're getting the most current. That might be a final question, because your impedance is at its lowest there, okay? Because if X of L and X of C cancel each other out, okay, because X of L and X of C are equal, okay, at resonant frequency, that means the only functional resistance in the circuit is coming from the resistor, okay, because they're canceling each other out. So kind of keep that in mind. And I know that's kind of complicated to wrap your head around, but we're going to work on it, okay? So here's just and the next formula that is very important. So first of all, this is what we've talked about in the series circuit. We've already calculated out our X of T. This formula right here for Z is so crazy complicated. We used to have to type this in before we had the ability to put a square root in a PowerPoint. But anytime you see this -1/2, that's a square root, okay? And this is just that formula kind of expanded. Now, the phase angle, as you guessed, and I kind of, the phase angle for when we're dealing with voltage is the phase angle equals tangent -1, voltage across LC, okay, over the voltage across the resistor, okay? And again, it's identical to this, right? If we just don't want to put VT down because that looks like voltage total. So we're putting the voltage of VT down there, okay? That's why this formula here, making sure we got this formula here is really important, all right? So, all right. And so before we do our examples, I do want to talk about the power formula here as well, okay? These are going to be the same as they've always been, okay? And I'll show you how these work here. But we have, our power across our inductor, all right, is going to be the voltage drop across LC times IT. Power across the resistor is going to be the voltage drop across the resistor times IT, okay? And the apparent power, okay? Remember, this can also be called true power as well, all right? This is going, there's a couple formulas for this, but we'll go ahead for simplicity purposes, say voltage total times I total, okay? Phase angle will be the same, okay? We will use, inverse tangent, okay? Px over P, PR, okay? All right. And then our power factor is the same as well, okay? Power factor is really important in here, and I think it's really cool. But it's PR over, APP, okay? So these are all the formulas that we need so far. Now, let me close this up here. Now, the last formula we need is to know when we are at our resonant frequency, okay? And this is a really important formula because this will tell us when X of L and X of C are completely canceling each other out, okay? And in that, it will also tell us when VL and VC are totally canceling themselves out, okay? And so the formula for this is, and this is the same for series and parallel circuits when you have all three components in here. FR equals 1 over 2 pi and the square root of L and C. Now, this is not X of C and X of L. This is the inductive value in henries and the capacitive value in farads, okay? So be aware of that. All right, let's go ahead and run this formula one time. And how you do this formula is going to depend on your calculator, all right? So here I have 330 microhenries. Okay, so let's go ahead and run this through the formula here. So again, let's just see how it goes. We'll do, so it's so it's microfarad, so it is 0.00033 times pico, which is to the negative 12. And if I come over here, that would be 1, 2, 3, 4. So I have 8, so point 1, 2, 3, 4, 5, 6, 7, 8. That would be 9, 10, 11, 12. So I'll just drop in the 2 here. That's what it would be, 2,000 picofarad converted over, equals, all right, I'm going to take the square root of that. Then I'm going to multiply it by 2, multiply it by pi, equals, and then I'm going to inverse this whole thing, and I get 195,906. So I'm going to come over here, and there we go. They went ahead and round that up to 196 kilohertz, okay? And at that point, X of C and X of L, that's exactly where it is. So what does that mean? If it is below that frequency, the circuit is capacitive. If it is above that frequency, the circuit is inductive, meaning you get more voltage drop across the inductor, okay? When it is at this frequency, the circuit is resistive. It is a purely resistive circuit, okay? All right, so think about that. So let's say it's 100,000 hertz, okay? That means it's capacitive. If it is at 250 kilohertz, it's inductive, meaning you get more voltage drop across it. And that's how the resonant frequency operates, okay? So this chart here shows you that, okay? As your frequency increases, your X of C goes down, your X of L goes up, and right when you get to this point right here, you are at resonant frequency and they are equal. Now notice your Z is at its lowest point. So that means your IT, if you were to draw a curve, it would look like this right here, okay? So let's review real quick a little bit about the resonant frequency. Capacitive inductive reactance are equal. Okay, so your X of T over here would be 0. All right, your voltage across your LC would be 0. Okay, your total impedance is as a minimum, and so is your resistance. Okay, kind of saying the same thing there. Your Z is at its minimum. The current is at its maximum. All right. Okay, again, there's an inverse relationship there. The phase angle is 0. Okay, so that means your power factor is at 1. Okay, all right, you'll calculate that out in lab, so be aware of that. All right, and so this is the formula for that. All right, and so when we come back to this, that's the end of the lecture. Yay, under 25 minutes. Okay, I'm going to give you a couple of examples of how these work. All right, okay, so thanks for watching, and I'll have those examples up. Make sure you save this. Okay, because we're going to need all of this. And again, this is no real new math besides besides this right here, besides your resonant frequency. Everything else is basically the same formula, with the exception of that and the idea that you just have to subtract the voltages in your X of L's, X of L and X of C. So yeah, I think it's pretty straightforward. So yeah, anyway, if you have any questions, please let me know, and I'll have those examples up. Go ahead and go to those examples now. Thanks.